Okay, hi everyone. Let's continue with partial derivatives. And then in this lecture, I will just give you more examples on partial derivatives. Example 1, you give in a partial function z. You see z is a function of x and y, function of at least two variables x and y. And then you want to find a partial derivative of z with respect to y. Z is a function which is e to the power of x minus y minus sine inverse of x squared over y. Okay, so here we want to find a partial derivative of z with respect to y. So we're going to derive our z with respect to y. Okay, and treat x as a constant. So let's derive z with respect to y. Let's go to the first term. You see, we want to derive e to the power of a function. You know, a derivative of e to the power of a function is e to the power of a function times a derivative of the inner function. My inner function is x minus y. When you derive this inner function, remember you derive it with respect to y. So you treat x as a constant and y as a variable. So derivative of this inner function would be 0 minus 1. Because x in this case is a constant, so the derivative of x is 0. That's why the derivative is 0 minus 1, because the derivative of y would be minus 1. So we multiply by the derivative of the inner function, which is minus 1. So the derivative of e to the function is e to the function times the derivative of the inner function, which is minus 1 if we derive the inner function with respect to y. Okay, minus a derivative of the second term. It's sine inverse of a function. It's a function of a function. So we have to apply the chain rule in this case. But when we're deriving sine inverse of a function, we use this formula for a derivative of sine inverse of x, which will be given during the test. So you know a derivative of sine inverse of x. I'm sorry about this. Okay. The derivative of sine inverse of x is 1 over square root of 1 minus x squared. So the derivative, when you have x here, the derivative of sine inverse of x is 1 over square root of 1 minus x squared. But here we want to find a sine inverse of a function, a function of a function. So you see we use this derivative. Instead of x, we're just going to substitute this function here instead of x, and then we're going to find the derivative of this sine inverse of a function. Because there's an inner function here, so we need to multiply by the derivative of this inner function after we substitute this function here instead of x. Okay, so this formula will be given to you if we know we're going to use it. So let's apply this formula here to find the derivative of sine inverse of this function. What we said, we're going to substitute this function instead of x here. So the derivative of this will be 1 over square root of 1 minus. So instead of x, where there's x, I will substitute this function here. Because we have this function which is x squared over y. X squared over y. That is also in squared there. Because we substitute the function and then we apply the chain rule, so we need to multiply by the derivative of the inner function here. So the inner function is x squared over y. Remember, what we're solving here, what we're finding here, we find a partial derivative with respect to y. So whatever you derive with respect to y. Eh? So times the derivative of the inner function, but with respect to y. So we treat x as a constant. So we don't use x. So let's leave x squared, but let's derive y. So before I derive y, I know 1 over y, I can write it as y to the power of minus 1. Eh? This 1 over y, I can write as y to the power of minus 1. So I'm deriving 1 over y, which is y to the power of minus 1. What I do here, I take this, and we just know y to the power of minus 1. I'll take, when I'm deriving y to the power of minus 1, I'll take this minus here, and then from minus 1, I'm deriving here. So I will have minus 2 here. Okay, so this is my derivative. Let me remove this so you won't be confused by all this. We'll use this now. Okay, let me repeat what I said. You're given a function of x and y, which is e to the x minus y, minus sine inverse of x squared over y. You want to find the partial derivative of z with respect to y. So what you do here, we derive this function with respect to y. We started with the first term. We see we have a e to the function, the derivative of e to the function, it's e to the function times the derivative of the inner function with respect to y, because there's a partial derivative with respect to y and treats x as a constant. So the derivative here, it would be minus 1. Because x is a constant, this would be 0. Y is a variable, derivative of y is minus 1. Okay, that's why we have minus 1 here. Going to the second term, derivative of sine inverse of a function. We used a formula for a derivative of sine inverse of x. So in that formula, where there's x, we're going to substitute x squared over y, the inner function. That's what we did here in that formula of sine inverse of x. But because we have an inner function, we apply the chain rule times the derivative of the inner function, but with respect to y. So x is a constant. That's why we return x. We're not interested in x. We're deriving y, but y is in the denominator. It's like we have y to the power of minus 1. So we're deriving y to the power of minus 1. So if we take minus 1, we're going to have this negative, and then y to the minus 1, the minus 1 in the exponent will minus 1. So that's why we have to the power of minus 2 here. So this is our derivative of 1 over y. Okay. So the next step is just simplification here. Okay. So let's simplify our derivative that we found, which is partial derivative of z with respect to y. So the first term is minus e to the x minus y. You see this negative here. And here, there's a multiplication. So this negative times this negative would give you positive. And here in the numerator, we have x squared over a denominator. Okay, let's start this. This is going to the denominator, but y squared there. So let's start by writing y squared here. And then here we have square root of, okay, this is x to the power 4 over y squared there. So this would be y squared minus x to the power 4 over y squared there. Also this y squared is under the square root. All right, let's continue and simplify our function. We note with the first, about the first term. We have minus e to the x minus y. We return our first term. The second term, if we look here, we use the first that you know from exponent. If you have a squared over b squared this will be square root of the numerator over square root of the denominator, and then b squared. Let's say b squared. Okay. So this square root is going in the denominator and numerator. Né? So we're going to have a squared all over. Let's return other term and focus here. We're going to have a square root of the numerator over square root of the denominator. Né? But we're going to have a square root of y squared. Square root and squared will cancel. We have over y. And that over y can go to the numerator, right? If you use the simplification, this is grade 10 work. It doesn't have even marks, so I just took that y that is in the denominator here and go to the numerator. You should know why. It's just a part of the simplification. So let's write the final answer now. The final answer is minus e to the x minus y plus, you see you have y divided by y squared, so 1y will cancel with 1y here in the denominator. So in the numerator, we're left with x squared over 1y. You have only 1y, square root of y squared. Oh, this is to the power 4. X to the power 4 here. Minus x to the power 4 here. Okay. Yeah, this is the final answer. This is a partial derivative of z with respect to y here. Okay, we're deriving this function and then okay, we got our derivatives. All right, let's do example 2. Example 2. We also did this example today, this day. If z is equal to ln of a square root of x squared plus y squared plus half 0.5 0.5 tan inverse of y over x. This is my function. If z is equal to this function of x and y, you give in this function, and the question, let's say, show a second partial derivative of z with respect to x if you add with the second partial derivative of z with respect to y twice, is going to be 0. Okay, so you're given a function z, you want to show this sum of those second partial derivative, the first one with respect to x. If you're adding to the second partial derivative with respect to y, you're gonna get 0. So what I will do here, I'll take the left hand side and show is equal to the right hand side. But on the left hand side, I have second partial derivative, so I'll need second partial derivatives. So I'll find those second partial derivative from z. So I'll need to derive z twice to find, with respect to x, to find the second partial derivative with respect to x. And then also for the second term, I'll need to differentiate z with respect now to y twice, and then to find the second partial derivative of z with respect to y, and then I will add them and see if I get 0. Ne? So let's do that as a part of the solution. So I always, if I see a log property, I always apply a log property first to make my life easier. So I know when I derive the first term, I have ln of a function, ln of a square root. So I will have 1 over square root of x times derivative of the inner function, which involving the square root. So it's better to put your function, if you have log function, apply the log properties first. So in the first term, you see this x squared plus y squared is to the power of half. You have ln of something that is to the power of half. With the log property, you can take this power half down here, right? So, which means I can write z as 1 over 2 ln of x squared plus y squared, okay? Because I take this half, which is the square root, here in my first term. Let me write the second term, 0.5. I can write 0.5 as 1 over 2 is half. I have tan inverse of y over x. So this is my function so far. But engifuna ukwenza is to derive, finding my first term first. So, and substitute in my left hand side and show is equal to the right hand side. So first let's find the second partial derivative with respect to x. So I'll need to find the first partial derivative with respect to x first before I find the second partial derivative with respect to x again. So let's find the first partial derivative with respect to x. So let's derive the first term. This is going to be half. I'm deriving now ln of a function. The derivative of ln of a function is 1 over that function times the derivative of the inner function, but remember with respect to x. So we times 2x because we're deriving x, y we treat as a constant, so the derivative of the second term will be 0. That's why we have 2x here, okay? This is the derivative of the first term plus 1 over 2 and derivative of tan inverse of a function. The formula for derivative of inverse of trig and inverse of hyperbolic function will be given. So the formula that will be given is this function formula. Let me write it here. A derivative of tan inverse of x is 1 over 1 plus x squared. This is the formula that will be given to you. Tan inverse of x, instead of x they have this function y over x. So to evaluate this derivative, where there's x here, you're going to substitute y over x. Y over x where there's x everywhere. And then don't forget, you apply a chain rule, so you need to multiply by the derivative of the inner function at the end. Always if you have a function instead of x. So let's apply this formula here in my second term. So where there's x here, I'll substitute y over x. So this will be 1 over 1 plus y over x, but in squared. Okay. Where there's x, I substitute y over x in my formula, because instead of x here, I have y over x. But because I have an inner function, multiply by the derivative of the inner function. But never forget, because this is partial derivative, you need to know you derive the function with respect to x because I'm finding the partial derivative with respect to x. You see? So when you multiply by the derivative of the inner function, remember I'm deriving with respect to x. So we treat y as a constant. So let's leave y as a constant and deriving x. We're deriving 1 over x. So x is to the power of minus 1 if we take x to the numerator. So when you're deriving x to the power of minus 1 here, it's going to be minus x to the minus 2 because from minus 1 as a power, so you minus 1, so it will be minus 2. Okay, so this is my first partial derivative because here I need the second partial derivative. I know I'll find my second partial derivative. Okay. I need my second partial derivative. I'll find my second partial derivative from my first partial derivative. So I'll need to derive this again. But before I derive it, I'll need to simplify my function because it's messy. To find my second derivative in my function look like this. So it's going to be a mess. So let's simplify first before we find the second partial derivative. Okay, let's simplify our function. You notice here 2 divided by 2. So in my first term, I will have x over x squared plus y squared. In my second term, this positive multiply with this negative, I will have a negative. Okay. And then in my numerator, I have y. In my denominator, I have also this x squared, because this is to the power of minus, so I'll have x squared. So let's write this 2 first, and also this x squared if it's going to the denominator. And now let's focus here. You see you have y squared over x squared, and then you add with 1. So this would be x squared plus y squared over x squared. If I'm adding this to the same, I will have x squared plus y squared over x squared, and this x squared can go to the numerator here. Okay, like this. And then let's continue and simplify this. So this cancel with this term. I'm simplifying my first derivative here. So I will have x, returning my first term, x squared plus y squared minus y over 2x squared plus y squared. This is my second derivative. My first derivative, I'll simplify it before I find my second partial derivative. So let me add this. So in thinking let me make my denominator a funny. So I'll introduce 2 over 2. So like I introduce 1 2 over 2, cancel with 2 over 2. What's being go find my denominator so I can add my numerator. So because this is the fraction, so the answer is just over same denominator. Okay, and just adding the numerator. So this is my simplified first partial derivative with respect to x. My aim of finding this first partial derivative was to find, I want to show the left-hand side equal to the right-hand side. My left-hand side have a second partial derivative with respect to x. But I found my first partial derivative because I know from my first partial derivative I'll derive again and find the second partial derivative with respect to x. Okay, we find the first partial derivative with respect to x. This is my first partial derivative with respect to x. So I can find my left-hand side first term, which is the second partial derivative. You see, you still remember my first term on my left-hand side is partial derivative of z with respect to x. Now I will be able to find this first term. I'll go slow. Now I will be able to find this from the first partial derivative. And then the simplified first partial derivative with respect to x is this one. The first partial derivative with respect to x is this one. Let's go from here. Yes, okay, this is my first partial derivative with respect to x. Okay, and then I want to find now the second partial derivative with respect to x, which is my first term. Okay, I find it from, this is my first partial derivative. I'm going to find the second partial derivative with respect to x. From the first partial derivative with respect to x, this is the first partial derivative with respect to x. I would say this one. This one. Brings a simplify and so sum from my first partial derivative with respect to x. Now I'm going to find the second partial derivative with respect to x. So if I check my first partial derivative is a fraction, to find the derivative of a fraction, algebraic, quadratic fraction, algebraic, I will apply a quotient rule. A quotient rule say derivative of the numerator while I'm leaving the denominator, and then I say minus and leave the numerator, and then multiply by the derivative of the denominator and say all over a denominator n squared. So let's do that, finding the second derivative from the first partial derivative. So we're going to find the second derivative but with respect to x. So let's follow the quotient rule. Derivative of the numerator here but with respect to x is going to be 2, because the derivative of the second term is 0, y is a constant, so derivative of constant is 0. So the derivative of the numerator will be 2, while we leave the denominator we leave this denominator, but let me multiply 2 inside while we leave the denominator, which is 2x squared plus 2y squared minus, now we leave the numerator, which is 2x minus y, while and multiply by the derivative of the denominator, but with respect to x. Whenever you're deriving, remember that you're deriving with respect to x. So the second term here would be 0. Here it will be 2x, but 2x multiplied with this 2 is going to be 4x. And then quotient rule say all over a denominator n squared. So you're gonna have 4 x squared plus y squared n squared. Denominator, everything you should be in squared here. So this is my second partial derivative, but let me simplify it and then go and find the second term. Let me simplify my second partial derivative. So here, I will multiply 2 inside here. So I will have 4x squared plus 4y squared when I multiply 2 inside. And here, let me multiply this 4x and this minus in my first term. I will have minus 8x squared. If I multiply this 4x and this minus with 2x. And now let's multiply this 4x and minus to the second term, which is minus y. So negative times negative will be positive 4xy. This is my second partial derivative. Then add my brackets in my numerator and I will add that terms now. Okay. I'm simplifying my second partial derivative, that's all. So the second partial derivative will become 4y squared, and then we have 4x squared minus 8x squared. It will be minus 4x squared. And then we have this term, which is plus 4xy all over the denominator, which is 4x squared plus y squared. X squared plus y squared is to the power of 2. And you see here, we can simplify this further. You see, if I take 4 as a common factor, and that's 4, I divide with this 4. So all 4 will cancel. So I'm left with y squared minus x squared plus xy over x squared plus y squared all to the power squared, because this 4 cancel with the 4 in the numerator, right? So this is my second partial derivative with respect to x there. So which is the first term on my left hand side there. On my left hand side of this, we just find this now, first term of my left hand side. And then now let's find the second term, which is the second partial derivative with respect to y. Again, we're going to derive z twice with respect to y. Okay, so now let's do that. We just finished the first term. Let's find now the second term, and then we're gonna see if we add them, we get 0. If we get 0, and then we're gonna be correct. To show that the left hand side is equal to the right hand side. Then this is my second left hand side first term. Let's now find the second term, which is the second partial derivative. All right. We want to find a second partial derivative with respect to y, so we're going to need to find the first partial derivative with respect to y from z. Let me rewrite it here. Z is a given function, which is half after applying log properties x squared plus y squared plus 1 over 2 tan inverse of y over x. This was my given function z. Now we wanted to show the second partial derivative of z with respect to x plus partial derivative second partial of z with respect to y is equal to 0. Yes. This thing is too slow. I wanted to show the second partial derivative of z with respect to x squared. If we add with the second partial derivative of z with respect to y is equal to 0. Put this one. We already found the second partial derivative here. Now we want to find this second partial derivative. So I said, let me rewrite this done. So you can see Z. So we can find our partial derivative with respect to y. So this would be 1 over 2. Let's derive this linear of a function. It's 1 over a function times derivative of the inner function, but now you derive with respect to y. We treat x as a constant, so derivative of x squared will be 0, so times 2y in this case, plus 1 over 2 times derivative tan inverse of a function is going to be 1 over 1 plus this function, the substituting terms of x of this function instead of x in a formula for tan inverse of x, which would be given because we have an inner function here. Let's find the derivative of the inner function, but with respect to y. So when we derive y, it's going to be 1. We leave x, so we're going to have 1 over x. So yeah, this is my first partial derivative. Simplification next, 2 divided by 2, it will be y over x squared plus y squared. Y over x squared plus y squared plus, now here in the denominator we have 2. 1 plus y squared over x squared is x squared plus y squared, okay, over x squared, and this x squared can go to the numerator. You understand why? Simplification over x squared, this one. Okay. So when we simplify our first partial derivative, this will be y over x squared plus y squared, and then 1x cancelled with x in the denominator, so we're gonna have x over 2x squared plus y squared. Again, let me add these two fractions. So we get the denominator fine, but here I'm short with 2 in the denominator here, but if I add 2, I need to divide it by 2. 2 over 2 is it's be 1, but I'm a denominator say fine. So this will have the same denominator, which is 2 of x squared plus y squared, and then just add the numerator, 2y plus x. So this is my first partial derivative. It's simplified here, so it will be easy to find the second partial derivative, which is the second term. The second term here that I want to find, and then I will add with the second partial derivative of x, which I've already found on top there. So I want to show that the left hand side, if I add them, I would get 0. I keep repeating and remind you what I'm doing. Okay, so this is my first partial derivative now with respect to y. With respect to y. This is my first partial derivative with respect to y. So now let's find the second partial derivative with respect to y. We're going to derive the one that is simplified. So let's find the second partial derivative of z with respect to y again. So let's derive this. So this is a fraction. We apply the quotient rule. So quotient rule, derivative of the numerator, but with respect to y. So derivative of the numerator is 2. While we leave the denominator is 2x squared plus y squared. There, let's multiply 2 inside. Derivative of the numerator, which is 2, while we leave the denominator, plus is given multiplier or 2 apart with denominator. and say minus. Now I leave my numerator. And then times the derivative of the denominator, but with respective to y. You see the first term, it's a constant because x is a constant. So the second term is 2y. So 2y multiplied by 2, it will be 4y. Okay. We follow the quotient rule. Let's say all over a denominator in square. So we're going to have 4x squared plus y squared all squared. So this gives me, when I simplify this, I'm multiplying 2 inside, 4x squared plus 4y squared. When I multiply 2 inside in my first term, in my second term, let's multiply this negative and 4y. So I will have minus 8y squared, and then minus 4xy, all over a denominator, which is 4x squared plus y squared squared. Let's add like times here. I will have 4x squared and 4y squared minus 8y squared is minus 4y squared minus 4xy over 4x squared plus y squared squared. Again, you see I have a common factor of 4 in my numerator, right? I can take a common factor which is 4, and then that common factor and divide with this 4, so 4 will disappear. So I'm left with x squared minus y squared minus xy over x squared plus y squared squared, because this 4 is cancelled with the 4 in the numerator. After I take it as a common factor, I cancel. Okay, so now this is my second term of what I want to show. Second partial derivative with respect to y. Okay. Let's go back here. Now we can show the left hand side is equal to the right hand side. So now we can answer this question. The question will say show second partial derivative of z with respect to x squared plus a second partial derivative of z with respect to y squared is equal to 0. So what we do, we take the left hand side, which is the sum of this. So we can add the second partial derivative of x. Let's go and check what is the second partial derivative of x. So what I'm doing now. You see what is the second partial derivative of x? We find it here. We find it here and simplify. This is my second partial derivative of x. Okay. So let's go and write this instead of second partial derivative of x here. The second partial derivative of x is y squared minus x minus x. This thing is too slow. Minus x squared plus xy over x squared plus y squared, and then we said plus the second partial derivative with respect to y. Let's go and check that one. We find it like in any. Let's see, this was our second partial derivative with respect to y. We found it here, and then we even simplified. This is our second partial derivative with respect to y. Okay, let's substitute in our second term of the left hand side. Want to show this, we took the left hand side, we substitute the first term with the second partial derivative. Now let's substitute the second partial derivative with respect to y that I just show you now. We said it's x squared minus y squared minus xy all over x squared plus y squared all squared. Okay. Let's add this is our left hand side that we substitute the second partial derivative of x and y, and then we want to see if we get the right hand side, which is 0. So you see they have the same denominator, which is x squared plus y squared and then just add the numerator. You see when we add the numerator, y squared minus with y squared will be 0. And then we have minus x squared plus x squared, it will be 0. And then this xy minus xy will also be 0. So everything will be 0 in the numerator. So 0 divided by anything is 0, which is equal to the right hand side. Okay, there it. So now please try this. When I see you, I'll give you a solution. Let me give you an exercise again. Exercise. Try it. I'll give you the answer when I see you in class. Z is equal to 1 over x squared plus y squared y squared minus 1. So z is equal to 1 over x squared plus y squared minus 1. I want you to show that x times the partial derivative of z with respect to x plus y first partial derivative of z with respect to y is equal to minus 2z times 1 plus z. Okay. You're given z. Z is a function of x and y. You want to show that x times the partial derivative of z with respect to x plus y times partial derivative of z with respect to y is equal to minus 2z all into 1 plus z. So what you'll do, take the left-hand side. You see on the left-hand side, you need the partial derivative of x and partial derivative of y. And then you're going to find those partial derivatives from z that is given. And then show it's equal to the right. Just to give you a hint, you see z on the right-hand side is this function. So when you derive this, when you simplify, after simplifying, when you see 1 over this, you'll have 1 over this. Just know 1 over this is just z. So just substitute z for that. It will simplify to this. Okay. Thank you.